Isothermal batch reactor, part 1. In this video, we will cover an example of an isothermal batch reactor. The example tells us that we are doing a copolymerization of styrene and butadiene in an isothermal batch reactor, and asks us what the final concentration would be after 100 hours of operation. The reaction is given as S plus 3.2B goes to the polymer. The rate law is negative Rs is equal to Ks times the concentration of styrene times the concentration of butadiene, where Ka is equal to 0.036 meters cubed per kilomole hour. Some additional information on this problem is we start with 2,200 kilograms of styrene and 5,000 kilograms of butadiene. The reactor volume is 27 meters cubed, and we provided with the molecular weights of both styrene and butadiene. Assumptions that can be made for this problem is that the reactor is both isobaric and isothermal, and we can also assume constant density. Please take a second to pause this video and see if you can do the problem yourself. The first step to this problem is to start with an overall mass balance. This is the change in moles of S over time is equal to the entering flow rate of S minus the exiting flow rate of S plus the rate of generation. Since there is no flow in or out of a batch reactor, those terms can be eliminated. We are left with dNs over dt is equal to Rs times the volume. An equivalent mole balance can be written for butadiene. Our second step is to deal with the rate laws. The rate law was given to us for styrene as negative Rs is equal to Ks times the concentration of styrene times the concentration of butadiene. We need rate laws for both styrene and butadiene for the mole balances, and therefore we use relative rates of reaction. Recall that for a system of A plus B goes to C plus D, relative rates show that Ra over A is equal to Rb over B, which is equal to Rc over negative C, which is equal to Rd over negative D. So for our reaction of S plus 3.2B goes to products, we have Rs over 1 is equal to Rb over 3.2. And this results in Rb equal to 3.2 times Rs. The last thing we need to do is stoichiometry. Since our rate laws are in concentration and we are given moles, we need to set up a relationship. Concentration is equal to the total moles divided by the volume and the molecular weight of the species. Using this, we can find the concentration for both styrene and butadiene. At this point, all that is required is a differential equation solver such as polymath to find the final concentrations. The following equations are what are necessary to get a solution using polymath. As you can see, our code contains our differential mole balances with their initial concentrations for both styrene and butadiene, our rate laws for both styrene and butadiene, our concentrations, as well as any given constants. We must also put the initial and final times of the reactor. The initial time of the reactor would be 0, and the final time would be 100 hours. The developed concentration profile looks like this. We have both the concentrations of styrene and butadiene decreasing because they are both reacting irreversibly. The butadiene is reacting slightly faster than that of styrene, since our reaction was S plus 3.2B goes to polymer. So the concentration of butadiene is decreasing at a quicker rate. The final concentrations of butadiene and styrene should be given as 2.93 kilomoles per meter cubed of butadiene and 0.70 kilomoles per meter cubed of styrene.